So I'm going to be presenting a hypothesis on the hypothesis that explains how optimization occurs in simple genetic algorithms with uniform crossover. Now, uniform crossover was first used by Ackley in 1987, and it was since popularized by Saiswirda and others, and there are numerous accounts of optimization by genetic algorithms that use uniform crossover. And in practice, there is a finding that it frequently outperforms crossover with tight linkage amongst the genetic loci. Uniform crossover, I guess it's more an evolutionary computation term. It basically just means free recombination, and we'll go over what that is in a second, just to nail things down. Now, the thing about uniform crossover is that its effectivity cannot be explained within the rubric of the building block hypothesis, which kind of tries to explain what goes on in evolutionary algorithms with tight linkage between genetic loci. And no viable alternative hypothesis has been proposed to explain optimization in genetic algorithms with uniform crossover. So what I'm going to present is something called the hyperclimbing hypothesis, and it's an explanation for how optimization occurs in these simple genetic algorithms that use uniform crossover. So I'm just going to hone in on this scientific explanation and talk about that for a second. What do I mean by scientific? So there's one kind of approach where you say that, which is the logical positivist approach, which is proof or bust. Prove it or go home. And there the emphasis is on verifiability. No proof, no cigar. And then there's the Popperian method, which says that scientific truth is provisional, and the emphasis is on falsifiability. You're allowed to make a hypothesis, and as long as you can make testable predictions. If those predictions come true, then that lends credence to the hypothesis. And there's additional tightening, wherein if the proof, if what's predicted is unexpected, then the theory deserves more credence. So, for example, Einstein's theory of gravitational lensing was Einstein's theory of general relativity predicted gravitational lensing, which was completely unexpected, and then it was found to be true in practice, and that greatly enhanced the reputation of Einstein's theory of gravitational lensing. So we can ask for additional requirements here. We can say, well, I want to assume very little about the distribution of fitness. If you have a theory about how evolutionary algorithms work, you're going to make some assumptions about the fitness function that evolutionary algorithms encounter in practice. And we want to make sure that those are really, really weak, which is just Occam's razor applied to evolutionary computation. We want an upfront proof of concept. And so that's to avoid another Royal Roads moment. And that's kind of in genetic algorithm lore, where the Royal Roads was a fitness function that was tailor-made to play to the advantages of genetic algorithms with tight linkage. And on that fitness functions, genetic algorithms with one-point crossover, tight linkage, failed pretty badly. And that was kind of an embarrassing moment. So we don't want a repeat of that. We want to come up with a Royal Roads function that works in this case. And what would be really nice to have is that we can identify some kind of core computational efficiency at play. And I'm talking from a theoretical computer science standpoint, big O of something where you're working with a hard problem and you're giving bounds that are quite surprising. I'm going to do all of these things. The hyperclimbing hypothesis is that genetic algorithms with uniform crossover perform adaptation by implementing a global search heuristic called hyperclimbing. So that's the abstract heuristic. You can think of the genetic algorithm as the machine code, and we're after what is that abstract heuristic that it's implementing. So we're going to talk about the uniform crossover operator. We're going to describe hyperclimbing. We're going to show proof of concept, the royal roads basically, that genetic algorithm can implement hyperclimbing efficiency. And if we have time, then I'll talk about predictions and validations on max 3-sat and the spin glosses problem. So uniform crossover, it probably doesn't need very much explanation here, but I'm going to talk about it because I want to highlight certain symmetries of uniform crossover that get used in the in kind of the reasoning here. So essentially, you take two bit string genomes, you line them up. You have a string of random binary variables. If a binary variable resolves to one value, then you pick from the top row. If it resolves to another value, you pick from the bottom row. So you get a child genome, and you subject that to mutation. Mutation again can be modeled with random binary variables. If it's one value, then you don't mutate. If it's another value, then you mutate the bit. Now the key point here is that in uniform crossover, these x's that you use to do the crossover operation, they're independent. That's not true for one-point crossover or other kinds of crossover. These are independent in uniform crossover, and what that translates into is an absence of positional bias. You can arbitrarily permute the bits in a genome and then permute them back after crossover, and you won't have there's no issue with doing that if you use uniform crossover. And if, in addition, the random variables describing mutation are also independent and independent of the number of bits in your bit strings, then there's the case that if some locus in your population is immaterial to fitness, doesn't play a part in fitness. In other words, if your fitness function is sparse, it only depends on the values at a few loci, then you can splice those loci out, and what the dynamics you see after splicing them out will be the fitness dynamics you see after splicing those loci out would be what you would see with those loci present.
I'm sorry. Wouldn't you usually take these y random variables to be to be such that kind of you have a mutation with probability 1 over L? So that's not independent of L?
No, because then you can't splice them out, right?
No, but I'm not. I mean, I'm saying kind of take away what you do, but just look how people use mutation in evolutionary algorithms.
Some people mutate based on the number of bits in the genome, and I'm saying that's not the case here. You have the mutation has to be independent of the number of bits.
But what I'm saying is that everyone does take the L into account because you want something like an average that one bit flips or so.
Right, but in this case, we're not doing that. I mean, people do that for whatever reason. I'm saying in this setup, to bring out the computational efficiency, we're not going to do that, and that then allows us to splice out the loci that are immaterial. And basically, what I'm talking about, the splicing out business, is basically you're coarse-graining the dynamics. And so if you've got a setup like this, you can just kind of purely using a symmetry argument coarse-grain the dynamics of a genetic algorithm with uniform crossover. So what is the hyperclimbing heuristic? It's actually, it's cool in that it's stateable in terms of schema and schema partitions. All the old machinery that Holland developed is applicable here. But the sort of final story is somewhat different. And so the setting is that you've got search space, which maps, and a function, a fitness function that maps bit strings to real values. And in this case, the function may be stochastic, so you're not always going to get the same ultimate value given a particular bit string. We can talk about, and so given how does this work? There we go. Given bit strings of length L, we can define an index set which contains elements of in 1 to L. And this index set basically partitions the search space into 2 to the k schemata, where k is the cardinality of the index set. And let's just denote this partition by these double brackets around the index set. And so here's an example for I equals 3, 7. You're basically partitioning the search space into these schemata. Now the coarseness of this partition is determined by k, as you can see, and you're going to have L choose k schema partitions of order k. So that's because there are L choose k possible index sets. Now for a fixed value of k, this is bounded, L choose k is bounded from below by L to the power of k. And when L is a very large number, say 1,000,000, you're going to have even for very coarse partitions, k can be 4, you're going to have a very large number of coarse schema partitions. Just one other definition, and then we can get to the good stuff. So the effect of a schema partition is nothing but the variance of the average fitness of the schemata in the partition. And as you can see, as you start sort of removing elements from this index set, you're going to have a smaller and smaller effect, because you're basically averaging over stuff that used to be in separate buckets. So that's a basic definition of effect here. So how does a hyperclimbing heuristic work? What it does is, out of this potentially vast space of coarse partitions, it finds a coarse partition with a detectable effect. Now, intuitively, you might, when you're talking about this vast space of coarse partitions, and which are basically divisions of the search space, most of those coarse partitions are not going to have much of an effect. They're not, the fitness is not going to separate out nicely. But in a few cases, there may be coarse partitions where it does. The hyperclimbing heuristic will detect that, and it will limit future sampling of the search space to a schema in this partition with above average fitness. And in doing so, it basically raises the fitness of future samples, because you're limiting it to a schema with higher than average expected fitness. And what does limiting future sampling to some schema mean? It basically means that you are fixing the defining bits of that schema in the population. And now you can recurse and you can do the same thing over the unfixed loci in the population. So that basically, in a nutshell, is the hyperclimbing heuristic. Now, there's a key assumption here that when you fix certain, what is important is that there may be what are called conditional effects. When you fix a bunch of loci, you may now create a condition where certain loci, certain partitions have an effect, where before they didn't have an effect. So that's this case. That's something that I call staggered coarse conditional effects, and that's a weaker assumption on the distribution of fitness over search space than what the building block hypothesis assumes, which is unstaggered coarse unconditional effects. And these weaker assumptions are therefore more likely to be satisfied in practice, and that's good because we want to explain optimization in genetic algorithms with uniform crossover on the widest possible range of fitness functions. Now, the thing to point out is that what I've described here, the hyperclimbing heuristic, it's an example of what's called a decimation heuristic. And as such, it's in pretty good company because decimation heuristics, they're a class of heuristics that iteratively reduce the size of a search space by finding and fixing partial solutions. And there's no backtracking allowed. And survey propagation, which is the state-of-the-art solver for random satisfiability problems, really large random satisfiability problems, operates in this fashion by basically fixing loci one by one. So what I'm going to give you is a proof of concept here. And it's going to be interesting given the talks that we've had earlier in the week, because I'm going to talk about how an evolutionary algorithm with uniform crossover can solve sparse parities, which kind of goes against what we heard earlier in the week. But there's a way that it doesn't, that the efficient computation occurring here doesn't quite fit into Valiant's model, which is why it actually does occur according to Valiant's model. If it did fit in, then there'd be a problem with this work, clearly, because within that model, parity cannot be done efficiently. But out here, we'll find out that parity can be done very efficiently, in fact. So the setup is this. You've got the fitness of any particular bit string. So there are basically, this is the parity the parity learning parities problem. You've got 4 loci, so k is 4 out here, and if for any bit string, if the parity of the bits at those 4 loci is odd, then you draw the fitness of that bit string from this distribution. Otherwise, you draw it from this distribution. And these are just Gaussian distributions with, a mean plus 0.25 and minus 0.25 and standard deviation 1. And so again, the game is, these are the loci that matter, but the algorithm doesn't know that, and the algorithm's job is to identify which loci matter. Given, it can query and it can get values back, and its job at the end of the day is to say those red ones are the loci that matter here. Now, this parity learning problem is interesting because the naive approach of visiting loci in groups of 4 to figure it out, the time complexity of that is, it's bounded from below by L to the power of 4. And approaching loci in groups of 1 won't work. Approaching loci in groups of 2 won't work. In groups of 3 won't work. If you're trying to search for expected marginal fitness, you have to visit in groups of 4. And so what I'm going to show you now is what happens when I run a population. It's very simple genetic algorithm, uniform crossover. It's got sigma scaling and stochastic universal sampling, which are pretty standard operations. What you're going to see here, I'm plotting the population here, and what you're seeing is the marginals at each loci. So it's the number of ones in the population at each locus is what. So these dots are going to move up and down as the frequency of the number of ones changes as evolution proceeds. The red dots are the relevant bits of the parity function, and we want the genetic algorithm to identify them. Oops. So here we go.
I'm checking to see if you had exponential time left.
So boom. The important thing, so now you can just go and read off the location of the parity loci. And it happened in 500 generations. Now where is the efficiency? This is just one run, So what I'm going to do here is I'm going to tack on another 800 loci. So I am vastly increasing the number of coarse schema partitions of order 4. And let's see how long it takes to find those, the parity bits. Again, within under 500 generations. Yes?
Did you watch Andrew Wan's talk yesterday?
Yes. I didn't watch it, but I read about it. I read his paper before.
So he has a proof that this works, right? That there is a polynomial time algorithm.
That there is a polynomial. This is polylogarithmic. Actually, I have a proof that you can do this in polylogarithmic time, in n, the number of the number of loci.
For hidden parity.
It's not
okay.
published, but. Mm-hmm. So here's I'm adding. So then now I'm looking at 10,000 loci. So vastly again increasing the number of coarse partitions, and again it will identify the parity bits in under 500 generations. And so, what's the deal? Because, Valiant's folks said that, you can't do parity with evolution, and here I'm saying you can. And the difference is that I'm doing something which I don't know whether it's quite allowed in Valiant's model, which is I'm looking over the entire population. And Valiant, you're limited to looking at the fitness of each individual point. Again, and also my points out here are just bit strings, whereas Valiant's points are hypotheses about Valiant's point. Valiant's. What's that?
I mean, the point is that you don't just answer statistical queries about your. You can do much more. Yeah. So
yeah.
Also Andrew Wan's model is.
Doesn't fit into the Valiant model. I see. Yeah, I definitely want to talk with him.
Andrew Wan's model solves every Boolean.
Right. Okay. Right. Yeah, I know. I'm definitely going to look him up. So now to take this idea and show you hyperclimbing in sort of full generality. What I've been trying to do is just to show you sort of the basic. The smallest, the computational efficiency in its most basic form, and here, I want to show it to you in full generality. And so the setup here is that, if you've got two matrices, if the third, 87th, and 93rd loci are 1, 0, 1. Then draw the fitness from this distribution. Otherwise, draw the distribution. Otherwise, draw fitness from this distribution. If, in addition, the 42nd, 58th, 73rd, 72nd loci are 1, 0, 0, 0, then draw fitness from here. Otherwise you're stuck here, and so on and so forth down here. And I call these staircase functions. And when you take this high-dimensional space, there's a way you can use something called dimensional stacking and view it on a two-dimensional plot, and it looks something like this. And of course, you can play with the signal strength. You can change the sigmas, okay? And so you can sort of play around with this. And so here it is a genetic algorithm with uniform crossover on one of these functions. And so you can see it finds the first set of dots, it finds the second, and so on. And of course, I've lined these dots up, but they need not be lined up. They could be in this fashion, and still the genetic algorithm will sort of identify the right partitions and hone in on a particular piece of the search space. And here it is with 5,000 loci. And so basically the irrelevant loci just don't, pretty much don't matter to the genetic algorithm. It is able to efficiently evolve despite the existence of a lot of irrelevant like dimensionality, you could say. Okay, and the rest of it is prediction validation, which I'll spare you. But I make a prediction, I validate that it's true on MaxSat and the spin clauses fitness functions. And you can look that up on my blog. It's called Evorhythmics. Just Google Evorhythmics. And I'll stop there. Thank you.
Questions for Keki?
Yes?
So there's a lot of population quantitative genetics theory that's sort of relevant to this. So I bet that because you've got what you call uniform crossover, which is basically very weak correlations, it's very high rates for a combination.
No correlation, basically. No linkage between.
There's some correlation because you're only breaking down associations by a factor of 2 every generation.
Okay.
So it's basically, you can ignore it.
Mm-hmm.
So then you write down the allele frequency dynamics, which is what you're doing. Presumably, have you tried writing down the differential equations for the rate of change of allele frequencies? Because that's what it looks like.
I haven't.
Because that will predict the rates in some detail. So that's one point. And the other point is that you mentioned, I wasn't sure I got the hang of the schemata and so on, but it sounds a bit like Fisher's fundamental theorem, right, which says that the change in mean fitness in one generation due to selection is equal to the total genotypic variance. And you can split that genotypic variance up into an additive effect, which is what is responding to selection in this case where it's only the allele frequencies that are changing, the correlations are distant. And then you also have a whole lot of other variance components, which are due to pairwise, three-way, whatever. And these are something like the variances across the schemata. But those dissipate very quickly. So you can isolate the component of progress, if you like, increasing average fitness.
What dissipates quickly? Are you saying that the interactions dissipate quickly?
There's a response in that what selection does is increase the frequency of the single bits.
Yes.
It's also increasing the frequency of pairs and the tree and all these other sets, but they're all broken up and stirred away by the recombination, by the crossover.
Right.
And so basically what the Fisher theorem is saying is that there's an immediate response due to all of the variance components. Then everything is complicated due to the higher level
second order and
thrown away, and you're left with just this additive variance. And then that should predict how long it takes to get to these.
Right, and so I would say that this almost says that you can have cases where there's with the parity basically there is no additive, there are no first order effects, there are no second order effects, there are not third order, there are only fourth order effects. And so
initially it's sitting there, it's absolutely at an unstable equilibrium in the way you set it up.
Yes.
And then the delay is mostly fluctuating such that one arbitrary combination of bits of the selected loci gets going.
Yes.
And then once those are at higher frequency, then they have a marginal effect proportional to deviation and it exponentially
Yes.
compensation. So that's
yes. Yeah. So, but at the beginning, yeah, in a dynamic way, yes, you do then have these effects, even first order effects. But at the beginning, if you're sampling from a uniform population, there are no, first, second, third order effects.
But you're relying on stochastic fluctuations to generate
Yes.
larger effects.
Yes. Yeah, that's why this wouldn't work with an infinite population model.
And it will be expensive in the computing as well.
Sorry, when I said that one's algorithm is polynomial, I meant polynomial in 4, not n.
Polynomial in 4.
Yeah.
Okay. Oh, all right. And what is it in n?
I guess no. Actually, n does not play. It's completely.
Interesting. Okay, I definitely need
It is
to.
irrelevant.
Yeah, it's
It's
n
just
0. Yes.
I think that's the problem, that you're not really, I mean, you started off saying you want to investigate why crossover is useful in genetic algorithms, but then what you're doing is not really a kind of an optimization problem. Your original optimization problem basically just has two fitness levels, namely kind of 0 and 1, depending on whether these 4 bits are even or odd parity.
Mhm.
But what you're doing is what you're aiming at is something more than optimizing this problem, because you're trying to find where these 4 bits are.
Right. So what I'm saying is that in the solving of the optimization problem, there is a learning problem that gets solved repeatedly, and that learning problem doesn't have to do with optimization. It has to do with identifying bits, identifying loci that are relevant and fixing them to some particular values. And so you have the repeated, solving of a learning problem, which, whose ultimate effect is, I wouldn't say optimization, but just adaptation, because we know that these things aren't necessarily geared to find the global optima in any way. I'm after how does adaptation occur, and what I'm saying is it's through this repeated solving of this learning problem.
Yeah, because I think most people would see genetic algorithms as optimizers for whatsoever optimization problems. This is why kind of maybe your title might be misleading.
Well, my title said adaptation, explaining adaptation in genetic algorithms with uniform crossover. Yeah. I mean, I think it's even stuff like first hitting time and things like that. I think it might be barking up the wrong tree a bit, because we don't expect evolutionary algorithms to find optima. Often we apply them to NP hard, NP complete problems where we know it's going to be exponential. So focusing on how long it takes to find a global optimum seems to me to be, kind of a little bit misplaced.
Great.